Okay. Hello, everyone. Good afternoon. It's time to start our today's Astroph. Today we have three presenters, Terry, Vignesh, and Betty. Who wants to go first? Okay, Betty.
Okay, today I'm going to talk about another benchmark, but it's basically focusing on AI for science and specifically on physics research. So, in abstract, just to talk about everything first. I mentioned that current scientific benchmark remain confined to domain knowledge, comprehension, and complex reasoning. It basically focus on like some ground truths and like calculation only. So it doesn't contain like the ability. It doesn't evaluate the ability on the real world research. So this paper aims to test the model's comprehensive domain knowledge, like and complex reasoning and the verifiable end-to-end workflows. And this paper's benchmark is constructed from 100 papers from physical review letters since August 2025. And also it is validated by domain experts. And there are 5 topics: astrophysics, condensed matter physics, high energy physics, quantum information, and statistical physics. So the main discovery about after all the evaluating is that first they found out even the strongest models achieve overall scores below 50, and I'll talk about the reason why. And second, the fellows are dominated by conceptual and formulaic errors, and third, the explosion derivations can be unstable, like on the difficult test. Like they can repeatedly talk about um things that is like somehow different points, and they will do something when they're like thinking to keep everything looks like it's stable. And so this topic is about AI for science, and I think this is what OpenAI talk about. And actually, they disbanded the group in April this year, so it is sad. And they want to talk about this paper. Want to talk about to what extent can AI functions as autonomous scientific research, like how AI ability on doing researches. So it talks about some recent benchmarks, but it mentioned that actually most benchmarks are more Olympiad style evaluations. And so as human less exam, and this is ruled by Han. And it mentioned that the texts are actually well-defined problem settings with explicit objective. Like everything is so clear, and also the solution pathways is clear, and which is not basically the how the real-world research condition is. So they want to start with theoretical and computational physics, and ideal domain with rigorous reasonings. And it also talk about some existing physics benchmarks. So I'll just give it right now. Okay, this is it's talking about OpenAI frontier science, but I think they disbanded the group. And okay, so let's go below. Oh, here it mentioned that AI and system have begun to emerge, and mentioned like some of the such as Google defines science models, and also like some other companies science models. So benchmark is needed for this evaluation, like test the abilities of these models. And here are the topics: astrophysics, like on the black holes or dark matters, and this I just talked about, and statistical. It also includes many body dynamics. Oh, here is the test designs, and I think It is about like long horizon reasonings, and there is something that I found like new in this paper, and it's quite a new point. Oh, and I'll talk about it later. Is in the next page. Oh, here's an example of the test. So it contains like these parts, and it has a motivation, and the cortex is at a problem itself, and also you have to answer the questions. And they use LM as judge to grade everything, but there is some problems to LM as judge. But this paper didn't go deeply about the evaluation part, so I think it's not enough. But it's fine because a text design I think is good. And this is what I think is new. I marked it as green. It for the subtext like here, you have 1, 2, 3, 4. And this is the subtext. And how they design is that they make the subtext independent and heterogeneous. And it avoids forming a strictly linear dependency chain. Like the mistake in one of the subtext will not affect the other. So this vortex is like independent, and this evaluation will be like more valuable. And the answers can contain verifiable numerical values, analytical formulas, and like many other things. And but I think actually it's only using LLMs to evaluate. So actually, as many might know that actually when you want to compare two numbers with maybe like 6.9 and like 6.19, there's a possibility that AI says that 6.19 is larger than 6.9. So I think this is the problem of their evaluation design. And actually, they didn't do much about the evaluation part, so I don't know what they do. Okay, so to prevent information leakage, actually, they just banned all the search-related tools. But I don't think this is good because on real research, we can use search-related tools. Like we web search for some like methods. So I think this is also the reason why all the model scores below 50. Like they cannot do web search, they cannot like search for the tools. And what they do is like they evaluate, like they let the AI models to answer the question for 5 times and use LM as judge, and like they average the scores in the 5 times. So okay, this is how they score, and also the point of its test is 0 to 100. And they found out that all the scores are below 50, and it shows the limit of current LLMs in realistic research settings. Yeah, so maybe they cannot do multi-step derivations. And this is the result. And we can see that on Astro and on stats, all the models have like relatively lower performance. And we can see this in another graph here. Like this Astro and stats are like lower. So I think Astro is what researchers can work on. And they also analyze the results, like why the AI models was wrong, into like 4 categories. One is formulaic conceptual error, which is like the largest proportion. And it reflects the insufficient domain knowledge in physics. And second, the derivation error, which shows a deficiency in reasoning ability, like hallucinations. And third, there is calculation issues. And also, the answer could be incomplete. Like they might omit answers, partial answers, or failure to satisfy test requirements. And it reflects insufficient adaptation to long horizon tasks and context management. And I think this could be like a result of the way how AI models is trained. Like sometimes when like the producers train the AI, they might give AI partial points. So AI can possibly trying to like do partial answers to get like some partial points. And this might be a result of that type of training. And okay, so this is I talked about this already. And this is about derivation errors. Just skip this. Oh, this one. It says like in the incomplete. It says that unsupported assumptions are introduced to maintain superficial logical consistency. Like in every like failing runs, it just trying to do again and like doing wrong thing, but sometimes it is different and it might and it could be wrong and it just come up with some assumption or like formulas, but it is not correct. So it's like part of hallucinations. And I think this is also um, a behavior of how AI models is trained. They just have to come up something looks reasonable. And there is a possibility that the LLM must just give it points. And if those AI answer in that way. And okay, so this is the same here. It talks about the limitation of its work. Like since all the text is generated from the papers, it actually does not contain like falsifying incorrect hypothesis. Like it is only generated from the papers, like the result, the correct result. So like how to troubleshooting is limited in these papers. So this is a problem. And I think the second and the last problem isn't a big deal. So I think this is the biggest problem. And this is all.
Okay, thank you so much, Betty. Is there any questions or comments to Betty?
So maybe I missed the concept, but is it like similar to what we have from the notebook KLM? The other AI which Thomason used for reading paper.
Reading paper? No, it's not about reading paper.
But like, what's the input basically? So input is these papers, right?
Yes, this paper is used to generate a text. So let's go to the text here.
Right.
So like it might Python paper and it's about So first they find a paper and about this topics. And they generate this task. So the input, the question that the AI is trying to answer is this task. So the paper that it inputs is to create this task.
Right.
Yeah.
So basically they input this, say whatever paper is on archive, and they
Yeah,
put it on this LLM, and
Yeah.
then they create this, what's the motivation of this paper, or what's the task done in this paper.
Actually, motivation is not the main point. It's more about the task itself.
Right.
Yes.
And they are saying that when they try to create this task list from the paper,
Yes.
they have this kind of accuracy or score,
And
low score.
to generate the test, actually, like there is human experts that help, maybe filtering or either creating the task.
Okay.
Yeah, so this is how they generate the test, but I think this method is a little bit limited.
I also have a question. Are the prompt of the for the task the same for every paper or?
Yes. It put the prompt to evaluate here. This is a task and this is an evaluation. So the evaluation prompt is actually the same for each of the tasks. Yes, they put this test like to each of the questions, so it's great. Thank you.
Thank you so much. If there is no more questions or comments, we can move on to next presenter. Okay, Vignesh.
Am I audible?
Yes, but
Okay, let me
you don't
share the
have.
screen.
Oh, yes.
Okay. Let me share the screen. So, is my screen visible?
Yes, yes.
Okay. So, Yes, today I would like to talk about this paper. So, if you remember, this paper is the one that Techia-san mentioned in the group meeting this Monday. So, this paper talk about investigating whether the host galaxies of this particular type of supernovae lies in interacting medium. So we all know that I'll give a quick introduction about what is superluminous supernovae. So superluminous supernovae is a type of transient event that is similar to supernovae, but it has a higher luminosity compared to the conventional supernovae. So here you can see that in this paper what they are trying to say is that the luminosity of the supernovae is at least 10 times brighter than the peak luminosities of the commonly observed supernovae. And similarly to the commonly observed supernovae where we have type 1, type 2, type 3, blah blah blah, superluminous supernovae also has type 1. And if the particular superluminous supernovae is hydrogen free, then we call it as type 1 superluminous supernovae. So in this paper what they are trying to do is they are trying to figure out whether the host galaxies of this particular type 1 superluminous supernovae is undergoing any sort of major interaction or a major merging event. That is the main purpose of this paper. So yes, the reason is we still don't know what causes this superluminous supernovae. Just like FRBs, we don't know the progenitor causes, and people do different type of analysis. And major understanding is that this superluminous supernovae happens in low metallicity dwarf galaxies. So here they are trying to figure out whether this is the only prerequisite for having these kind of explosions, or merger can introduce star formation, and this star formation can also generate a superluminous supernovae. So they wanted to figure out whether this could be also the reason. So yes, for I'll move on to the data set. So for that particular data set, for that what they are trying to do is they are trying to take HST images of the host galaxies of this particular superluminous supernovae, and they try to draw a 5 kiloparsec radius, and try to figure out any if the host has any companion other galaxies within this 5 kiloparsec. And also they compare this with long GRBs. So the figure 1 shows the redshift distribution of GRB host galaxies and the superluminous supernovae host galaxies. So the basic methodology is this. If the maybe I can show the figure. Yeah. So this is the basic methodology. What they do is they take HST of host galaxies of superluminous supernovae. Here you can see there are 4 different examples. On the top left one, you can see that this green circle corresponds to 5 kiloparsec radius. Note that this is 5 kiloparsec, not megaparsec. And the reason why they chose 5 kiloparsec is that the virial radius of a typical dwarf galaxy is in the range of 5 kiloparsec. So that is the reason they chose this radius. And the box corresponds to the location of the superluminous supernovae. And if there is no host galaxy, for example, in this case the PTF 10VWG, in this event you can see that there is no host galaxy that is associated with this particular event. There is one within the 5 kiloparsec radius. And here on the right panel you can see that there is a host galaxy which is very close to this event, and this is likely to be the host galaxy of that particular transient event. So here's the catch. So if there is a companion galaxy which is very close within this virial radius and very close to the superluminous supernovae event, then they say that there is a chances of high chances of these two interacting with each other. So this is how they differentiate whether the host galaxy has a companion, major companion or not. So later they combine, they compare with three different set of control samples. Before going on into the control samples, this is the total galaxy that has HST images for their analysis. You can see that the total number of some complete sample is around 42. So maybe I can show the figure. Yeah, the figure 2, sorry, figure 3, you can see that this is how they generate control samples. So they generate control samples by two methods. Both of them uses Monte Carlo approach. And method one, what they do is, now in a particular image they have a lot of galaxies, right? Like these are the, each dot corresponds to the galaxy here. And what they do is they figure out whether they take a random galaxy. Let's say they take one galaxy here, maybe I can show the cursor. Let's say they take one particular galaxy here, then they draw 5 kiloparsec radius and try to see whether there are how many number of companion galaxies within this particular radius. And they do it same for the same process, they do it 1,000 times and take a mean of that particular distribution. That gives you the average number of companion galaxies expected if we take a random 5 kiloparsec aperture in this image. So for the second method, what they do is they shuffle the entire positions of the galaxies. So we know we can obtain the coordinates of each galaxies using source extractor. And once we know the position of the galaxy, we can randomize the entire position, then repeat the same process. So by randomizing this, what we can say is that the average companion value that we obtain is not due to the we can differentiate whether it has any physical significance or it is due to a random coincidence. So that is the method that they use for control samples. So later they compare with GRB host galaxies too. So this table shows the average number of companions. So for the case of superluminous supernovae, the average companion they expect is 0.7, which means naively speaking, we can expect at least one galaxy that is associated with the major that is a major companion of the host. And this is the random object comparison and random coordinates. So random coordinates means when the coordinates are changed randomly. And when they compare it with GRB, you can see that the superluminous supernovae has a more higher chance to undergo merger compared to GRBs. So yes, I'll go to this figure. So yeah, this is the cumulative distribution on the left panel, which shows the number of companions within the 5 kiloparsec. You can see that the green color corresponds to the number of companions, I mean sorry, number of companions of around superluminous supernovae host galaxies. And the panel on the right shows number of companion changes as a function of radius. So if they take 1 kiloparsec radius, what would be the average number of companion expected for each object? And 2 kiloparsec, 3 kiloparsec, you can see this is the distribution on the right side. So the same panel is shown in the left. So you can see that as the separation increases, the cumulative fraction of number of companion galaxies also increase for superluminous supernovae. But the when you compare this with the GRB host galaxies, you can see that the rate of companions is very high for a superluminous supernovae compared to the GRB host galaxy. So from this, what they are claiming is that, to conclude my talk, what they are claiming is that they figured out that the average companion of superluminous supernovae host galaxies are at least 50 percentage, which means at least 50 percentage of the data set, around 42, which means around 20 samples has at least one major companion within 5 kiloparsec radius. Also from which they calculated the fraction of average number of companions, which turns out to be 0.7. This is very high compared to the random coincidence, as well as compared to the GRB host galaxies, which is 0.44. So also they wanted to figure out, even though they see a difference between superluminous supernovae host galaxies and the random, they wanted to take whether this is significant or not. To check it, they performed AD test, and the p value is less than 10 power minus 3, which means that the number of companions around superluminous supernovae is physically significant and statistically significant compared to the random distribution. So yes, to conclude this paper, what they are saying is that superluminous supernovae event, these host galaxies are often found in interacting environments, and their interpretation is that even though low metallicity is a prerequisite, we cannot say that this is the only sole prerequisite that is required for these kind of events to happen. And these major interactions could trigger star formation, and these star formation also could start the starburst phase with the within superluminous supernova explosion. So yes, this is what I wanted to say in this paper. So the main reason I took this paper is because I think we can do the same for FRB host galaxies as well.
Okay, thank you, Vignesh. Is there any questions or comments to Vignesh?
Hi, Vignesh.
Yes.
So, if I see figure number two, um,
Okay.
so first of all, this is only HST data, right?
Yes.
So this is only optical galaxies they are talking about.
No,
But what
actually,
if
these
there?
are UV. Sorry, I didn't mention that. These are they only take rest frame, the galaxies which has rest frame UV wavelength that is less than 4,000 Armstrong.
Right, but then what about the galaxy? Like, suppose we had more data, like JWSTIR data
Hmm.
or some, because there could be galaxies which are more like dusty galaxies present. Do we like,
Mm.
do rather rephrase the question? Do we have any statistical data which says that the dwarf galaxies or the host galaxies or supernova exist more majorly in UV galaxies?
I don't think so. I don't think so. They have those kind of data, but I'm not sure because I haven't know any previous papers on this kind of phenomenon. But I'm not sure about that.
Okay, maybe like when you do it for the FRBs, it would be good to check whether there exists like a data which says that the host galaxies exist either in some particular type of galaxy.
Mm-hmm. So for the case of FRBs, I think it's obvious because major studies what they are saying is that the FRBs are often found out in massive star-forming galaxies or yeah, star-forming galaxies are the predominant candidate for FRB host galaxies. Even though there is a non-zero possibility of other quiescent hosts, but major statistics is based on
Hmm.
star-forming galaxies.
Okay, but this then based on the redshift, that will also change, right? The band will
Yes.
change. So
Yeah.
yeah. The other question is if you see figure number five and figure number six.
Okay. Uh,
So the figure number five is basically just the histogram, and then six
yeah,
is
yeah.
the
Six
cumulative
is the cumulative
distribution.
distribution. Yes.
But if you see the random coordinates, it seems like when I plot the cumulative of this random coordinates, it would be much steeper and compared to the supernova, unless they are not weighing it for the radius. Are they weighing it for the radius? Because in the case of supernova, there is only like one bar which is sort of dominating the entire
Mm.
histogram,
Mm.
and
Mm, mm,
I
mm.
guess that's what causing the cumulative distribution to increase like this. But there should be like some weightage given to the
Radius of the.
hmm,
I
right.
I see. So, I think they don't talk about radius of the particular galaxy. So all they talk about is the radius of the aperture size that they have taken.
Aperture size.
Yes.
Okay.
Yes.
Hmm.
So
Okay.
yeah, I think this is interesting to check.
Hmm. Yeah. Thank you.
Thank you.
I have a question.
Yes, Tadaru-san.
Okay, so maybe you mentioned, but I think when they are, so my question is whether they are considered a slice of the redshift when they consider companion.
Uh,
Did they do that slice,
you,
redshift slice?
I think yes. I think yes, but
Ah,
I
okay.
need to verify
Hmm.
it once again. I
Ah,
saw it somewhere.
okay. Also, maybe related to the former question,
Mhm.
what about the completeness of the galaxy? Because dwarf galaxy is very faint, and the
Mm,
if you depending on the completeness, you can include many unresolved maybe dwarf galaxy if you have a better telescope. So I
mm,
think the number of the companion inside a fixed aperture at a given redshift
mm,
varies depending on the completeness. So I wonder how this can be done between, for example, different host galaxy. If you compare
mm,
superluminous supernovae with a random one
mm,
using the same control sample, it's okay. But I think comparison between superluminous supernova versus gamma ray burst is questionable because gamma ray burst is found relatively far
mm,
distance.
mm, mm, mm,
Yeah,
mm.
so I'm curious about this, and
Okay.
yeah, and
I-
also yeah, that's it basically.
okay.
Yeah.
So the for first question of a comparison between superluminous supernovae and the random galaxies, regarding the completeness, what they are saying is they are accepting the fact that the completeness plays a huge role in figuring out the significance. But
Mm,
what they do is the best effort they can do is when selecting the random galaxies, they
mm,
have a cutoff. So they know the this is the selection criteria they use. So the random object should be within 1.25 magnitude of the host galaxy. So basically they only take the random galaxies which are in similar magnitude range as the superluminous host galaxy. So they say that by doing this we may resolve this completeness issue a little bit, but still it is biased by the completeness. That is the only limitation they are saying in this method. And the second thing is that when they compare with the grb host galaxies, you can see that the p value is not that much significant. Even they are still bit skeptical about this particular comparison of superluminous host galaxy and the grb. So their result, what they are saying is that there is still some significant, there is still a loss of some significance between these comparison, and they are not sure whether this is the right way to compare grb host galaxy and the superluminous supernovae.
yeah, so I think they can only report the fraction. I think the number of galaxy are
Hmm.
for given completeness limits. So I think they should clarify this point. I think maybe they do.
Maybe they do. Maybe I have to read it carefully.
Then what's the conclusion? So if merger is driving the superluminous supernovae, these are these progenitors are found in the merger environment. But
Yes.
I think it's within the merger environment. It doesn't have to be inside a host galaxy.
Mm-hmm.
So it ejected from the one of the merger system,
No,
and it's
actually,
traveling. Mhm.
what they are claiming is that, so their possible theory is, so this merger can introduce starburst phase, right? Like after merger there is a starburst phase, and
Yeah.
beginning of this starburst phase we could expect these kind of superluminous supernovae events. So that is what they are trying to say.
I know, I know.
Mm,
However, the location you found these are superluminous supernova is not only within galaxy. It
mm,
is
mm,
traveling somewhere in the space.
mm, 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 mm,
There is no coincident galaxy in most cases.
mm,
So this event is happening at that location, but the formation of this progenitor is happening when a merger is happening, where star formation is triggered.
mm, mm,
So
mm.
do they kind of mention this kind of time delay and the travel from the
I
Earth
don't,
location?
I don't think so, Shatara-san. So
Okay.
they are that mergers could also be a prerequisite for these kind of events, and they are comparing it with the previous studies based on metallicity. So because their only purpose in this paper is to say that not only metallicity could be a prerequisite, also merger can also do these kind of superluminous events. So that is what they are trying to do say, and
Yeah.
yeah, that is the main conclusion of this paper.
Okay. Thank you.
Okay, thank you for the discussion. If there is no more questions or comments, we can move on to Terry.
So the paper I want to share today is about a close quasar pair in a massive galaxy merger at C equal to 5.7. So let's talk a little bit about the background. So the close quasar pair is a rare product of galaxy merger event in which two supermassive black holes are all actively accreting. But in the previous work, they found a lot of quasar pair, but the redshift only in the range of less than 4. And for the redshift range larger than 4, the number of quasar even smaller, because the quasar number density in the early universe will drop rapidly. But in 2021, in their previous paper, they proposed the first candidate of closed quasar pair in kiloparsec scale with a with z larger than 5, and they call this object J 20374537, and this is also the object they discussed in this paper. But the only problem in the previous paper is they cannot identify the nature of this object because there are two possible scenarios. The first one is this is the true closed quasar pair originated by the galaxy merger event, and the second scenario is this is the doubly imaged gravitationally lensed quasar of only one quasar. And to identify the nature of this object, in this paper, they used the ALMA observation in band 7 conducted in August 2022 with 4 different spectral windows at 4 different frequency listed here. And to do the data reduction, they used CASA, Common Astronomy Software Application, and also they use other tools to obtain a clean continuum image and also produce the C2 line emission, including the C2 moment zero map and also the mean velocity and velocity dispersion maps, which is shown in figure 1. So the upper left panel is the clean dust continuum image, and it shows a tidal bridge of these two quasars. So the southern one is quasar A, and the northern one is quasar B. And the upper right panel is the C2 moment zero or C2 intensity, because they want to integrate the gas intensities surrounding two quasar, which is not clearly shown in the dust continuum panel. And here you can see there's a irregular structure of quasar B, and from the the top two panel, they can obtain a first evidence of tidal bridge, which suggests the galaxy merger event for these two quasar. And to fully rule out the scenario of the lens quasar, they applied the lensing model. So they show in figure 3. So for the lensing model, so in figure 3, the top panel is for the continuum image, and the bottom row show the model of C2 line. And if this is a real lens event, you see the lens arc in the image, but there's no lens arc feature here. And also, there's inconsistent in terms of the position and orientation in the middle panel across different wavelength. So if this is the real lens event, you see the consistent in position and also the Einstein radius of these two panels, the continuum in 4 different wavelengths and also the C2 line. But here there's an inconsistent. And also the lensing model also suggests that the host galaxy of these two quasar have extremely small half-light radius, which is about 0.5 to 0.7 kiloparsec. For typical quasar host galaxy at Z higher than 6, the half-life radius should be larger than 1 kiloparsec. So from figure 1 and figure 3, they can make sure that this object is the close quasar pair originate from galaxy merger event, and it's not the gravitationally lensed quasar. In the figure 2, they use the extracted C2 spectra, and they do the fitting using the MCMC method to derive the C2 redshift. And you can see that the redshift of these two quasar are very similar, which is close to 5.7. And they use equation 2 and equation 4 to derive the Starforming rate and the dynamical mass of these two quasar, which is for the dynamical mass, these two quasar have the dynamical mass in order of 10 to 10 solar mass. And for the Starforming rate, they all have the Starforming rate higher than 500 solar mass per year. So next, they want to estimate the pair fraction, the quasar pair fraction. Previously, the quasar pair fraction for the quasar within the redshift range of 1 and 4 is only 10 to minus 3. And to estimate the quasar number fraction in higher redshift range, they first estimate the total number of quasar in the redshift range between 5.5 to 6 in the dark energy survey field where this object was detected. And then they calculate, they obtain the total number of quasar is 83. And then they infer the pair fraction, which is at least 1.2%. And this is why this paper is highly impactful, because they improve the lower limit of the number fraction of quasar pair compared to lower redshift range. So in comparison with the previous work, in Matsuka and Izumi et al., these two papers conducted the research focused on quasar pair at C equal to 6.05. But the star forming rate of this object is less than 100 solar mass per year, significantly lower than the star forming rate of the quasar pair in this work. Even though the quasar pair in this work is not the highest redshift quasar pair, but according to what they mentioned in a previous paper, the quasar pair at C equal to 6.05 will eventually reach the higher luminosity and higher star forming rate, which is similar to the quasar pair in this work. So I think that's all for this paper. I'll stop here and take your question.
Okay, thank you, Terry. Is there any questions or comments to Terry?
So they don't calculate the black hole masses, right?
Black hole mass? No, they only have the dynamical mass of the host galaxy.
Host galaxies.
Yeah, not the supermassive black hole.
But they do have the initial line of C2, so I think it would have been quite easy to calculate the black hole mass. Because they have the initial line. So I wonder why they do not calculate the black hole mass in this way.
Yeah.
Okay.
Let me check in the table if they mention or not.
Also, figure 4, they don't plot the previous.
Figure 4.
Like there are 6 quasars.
Oh, yeah.
So I wonder why.
Yeah, in table 1, they didn't mention about the black hole mass.
Okay, thank you again. If there is no more questions or comments, for tomorrow, Angel is already volunteered. We need 2 more volunteer for tomorrow. Okay, Changman, thank you. 1 more volunteer. Okay, thank you, Priyanka. Okay, thank you so much for your time. See you tomorrow at group meeting. Thank you. See you.